Quotient rule for derivatives says that if you need to take the derivative of the quotient of two functions whose derivatives you recognize or could find, so that you take the derivative of the top times the bottom minus the top times the derivative of the bottom all over the bottom squared. So, for example, if you wanted to take the derivative with respect to x of x squared minus 7x all over x cubed plus 5, you would take the derivative of the top, which is 2x minus 7, times the bottom, x cubed plus 5, minus the top, which is x squared minus 7x, times the derivative of the bottom, which is 3x squared, all over the bottom squared. So x cubed plus 5 squared. Now the calculus is done. We've applied the quotient rule, so we found the derivative. But anytime you're working with a fraction, it would be nice to leave that fraction in lowest terms. So let's first multiply this out and collect like terms and see if there's anything that we could factor in order to reduce. So we multiply this out. The top we have 2x to the fourth plus 10x minus 7x cubed minus 35 minus, if we multiply this out, we have 3x squared times x squared is 3x to the fourth, and 3x squared times negative 7x would be negative 21x cubed. This is all over that denominator, x cubed plus 5 squared. I won't bother to multiply the denominator out, since in order to get our fraction lowest terms, we're going to need to factor anyway. So go ahead and leave things that are already factored together. Here I had I had terms, right? Things that were subtracted in this case. And so I needed to multiply this out so I could collect like terms and see if that whole thing could be factored. Let's see, we have 2x to the fourth, and we have minus 3x to the fourth, so that would be a total of negative x to the fourth. What about our cube terms? We have a negative 7x cubed, and we have minus a minus, so that's plus 21x cubed. 21 minus 7 would be 14x cubed. So that takes care of this term and this term. And for x squared terms, we don't appear to have any. And for linear terms, there's just this one, the 10x. And for constant terms, we just have this minus 35. Okay, all over x cubed plus 5 squared. Okay, so looking at this, we would ask ourselves if we could factor this at all. If we factored negative 1 out of that, we'd have negative x cubed. We'd have x minus 14. But this, we couldn't make that an x minus 14, so we can't factor by grouping. I don't think that's going to be particularly easy to factor. And if we did, I don't think we'd have something that would cancel an x cubed plus 5 in there. So I think we're in lowest terms with this one. So that would be the derivative of that particular quotient. So again, the quotient rule says if you take the derivative of a quotient, you can do the derivative of the top times the bottom minus the top times the derivative of the bottom all over the bottom squared. All these rules just make it easier to take the derivative of a function. They go back to that limit definition, but they just make the job quicker. Here's an important rule. If you have a function that's an exponential function, it means you have some constant raised to a power. The exponential rule says if you need to take the derivative of an exponential function, you get the exponential function back times the natural log of the base. So for example, if you need to take the derivative with respect to x of 2 to the x, the answer according to this rule is 2 to the x times the natural log of 2. One common base is e. The derivative of e to the x would be e to the x times the natural log of e. But by definition, the natural log of e, that means the exponent you put on e to get e, which is 1. So this is e to the x times 1, be e to the x. In fact, that's one way of defining e to the x. E to the x is the function whose derivative with respect to x is itself that passes through the point 0, 1. That's a definition of e to the x that works. So it's the function whose derivative is itself that happens to go through the point 0, 1. Okay. What about derivatives of our trig functions? Well, it turns out that the derivative of the sine of x is the cosine of x, and the derivative of the cosine of x is the minus sine of x. If you have trouble remembering which one gets the minus sign, you could draw their graphs. So if you look at the graph of sine, and I'll just draw a quick graph of sine. The graph of sine looks like this. It goes up, down, and up again, like that. Now think about the slopes here. Right here the slope is positive, but the slopes gradually decrease until at this point the slope is 0. Right? Here the slope is actually a negative number, and then they become less and less negative, so the function starts to level out until right here the slope is 0, and then at this location the slope is positive again. If you look at that graph, you can see, oh yeah, it looks like the slope of the sine function is given by, this looks like the cosine, doesn't it? So just by sketching I can realize that the derivative of the sine is the cosine. That must mean the derivative of the cosine is the one that's opposite. But you could always check with a sketch. Look at the graph of the cosine. Here's 2 pi, here's pi, pi halves, 3 pi halves, and of course 0. The cosine of 0 is 1. At pi halves the cosine is 0. At pi the cosine is negative 1, and so on. So the graph of the cosine looks a little like this, right? If we look at the graph of the cosine and think about the slope, or the derivative, the slope here is 0, but now throughout here the slopes are all negative before the slope is 0 again, so the slopes must do this. Okay, over here the slopes are all positive, so they start out near 0, they become more and more positive till they reach sort of a maximum, and then they become less and less positive. So we get a function that looks like this. That's not the graph of the sine, because the sine should go up, down, and back. This one goes down, up, and back. That must be the minus sign. So you can tell from the graphs, actually, that the derivative of the sine should be the cosine. The derivative of cosine should be minus sine. Once we know those, we can find the derivatives of the other trigonometric functions. For example, if you want to find the derivative of the tangent of x, remember the derivative, remember the tangent is the sine of x over the cosine of x. So we can apply the quotient rule. We take the derivative of the top, the derivative of the sine is the cosine, times the bottom, minus the top is sine x, times the derivative of the bottom, the derivative of cosine is minus sine x, all over the bottom squared. So cosine squared. Of course, what we have here is cosine squared x, minus sine times minus sine makes plus sine squared x, all over cosine squared x. And remember our Pythagorean identity that says that cosine squared plus sine squared have the same angle as 1. So we get 1 over cosine squared x, or 1 over the cosine is the secant, so we could call this the secant squared of x. So the derivative of the tangent is the secant squared. What about the derivative of the cosecant? Remember, the cosecant is 1 over the sine. So we could apply the quotient rule. We take the derivative of the top. The derivative of the constant 1 is 0 times the bottom, minus the top, which is 1, times the derivative of the bottom. The derivative of the sine is the cosine, all over the bottom squared. That would be the sine squared of x. So we have negative cosine x over sine squared x. Cosine over sine is cotangent, though, so we have negative cotangent x, and there's one sine left downstairs, and 1 over the sine is the cosecant. So the derivative of the cosecant is the negative cosecant cotangent, or the negative cotangent cosecant. I'll let you apply reasoning similar to these two problems to show that the derivative with respect to x of the cotangent of x is the negative cosecant squared, and that the derivative with respect to x of the secant of x is the secant tangent. And you can just use the quotient rule together with the fact that the derivative of sine is cosine, derivative of cosine is negative sine, in order to prove these, just like we did there.